Hey guys, so today we're going to do a video about the basics of continuity and kind of just make it simple. It can be confusing when you think about the formal definition that I've got down here, but really continuity is something that you understand. You've been doing it for years now. And really, if a function is discontinuous, you can think about it as if I was drawing this graph, whenever I have to lift up my pencil to continue to draw it, it's discontinuous. So as I draw this, let's say I'm drawing it right here, I have to lift my pencil up, so it's discontinuous there. Alright. Still drawing, still drawing. Well, I got a hole. I got to lift up my pencil and fill in that dot. That's another discontinuity. And here I'm going down. Oh, got another one. I got to lift up my pencil. That's another discontinuity. Anywhere where I don't lift up my pencil is continuous. So that's just like the intuitive way to think about it. If you have a graph in front of you, then you can just think about it exactly like that. And then now let's look back at the formal definition and try to make sense of it. So this is it. For a function to be continuous, limit as x approaches a, f of x must be equal to f of a, which equivalently means, as the limit as x as it approaches a from the right, f of x has to equal f of a, and limit as x approaches a from the left, f of x has to equal f of a. Okay, so now let's take a look at the graph after reading that confusing definition. And it says the limit as x approaches a has to equal the point a. So let's take a look here. Let's say this point's 2. And let's take a look at the point 1. So we've got limit as x approaches 1. And first, let's make sure that limit exists. So to do that, we have to check limit as x approaches 1 from the left, f of x equals, well, as we're coming from the left side, we're going down. We're getting close to that 2. So that equals 2. Then for a limit to exist, the right-hand limit has to equal the left-hand limit. So limit as x approaches 1 from the right, f of x, so we're thinking about going up this way, we're still approaching that too. So that lets us say with confidence that the limit as x approaches 1, f of x equals 1. And now if the function is continuous, then f of x will equal f of a. And what that means is that the actual function's value at f of 1, because that's the point we're evaluating, should equal 2. If that's continuous. This limit is 2, not 1. My bad. So f of 1 is supposed to equal 2 if the function is continuous. But f of 1 is equal to 7. We have that up here. That's the point. So that means it's discontinuous because the limit as x approaches a, which is as f approaches 1, does not equal the point at 1. So 2 does not equal 7, discontinuous. And what we call that, I'll write that here, that is called removable discontinuity. I like to think about it as I could literally just pick up that one piece, pick that up, and I put it here instead. I removed it. And then now let's go to the second example. Let's go to example number 4. Not example 4, I guess, the point 4. So we're looking at limit as x approaches 4. So limit as x approaches 4. And for a limit to exist, we have to check left hand and right hand again. So as the limit as x approaches 4 from the left, we're going down here. We'll say this is negative 1. F of x is negative 1. And limit as x approaches 4 from the right, f of x equals, well, we're going from the right, we're coming down. We're getting close to that 7, so it's 7. So that means that limit as x approaches 4, it doesn't even exist. So how can the function be continuous if the limit doesn't exist? The rule is it can't. So that automatically tells me the function can't be continuous. Then another giveaway is that that has to equal f of a, which also doesn't exist. And we can't be like, oh, they both equal doesn't exist, it must be continuous. No, they have to be equal in terms of the number values. So here, both of them don't exist. So that's another discontinuity. And the way we call that one is we call that jump. It makes some logical sense to me because we're going from one point, we're kind of jumping up to the other one. So we're jumping up to the new graph, and that's what we're doing here. So, and then now we finally have a final type of discontinuity that we figured that out was at negative 4. So we can look at this here. We got limit as x approaches negative 4. F of x from the left, f of x is left, we're going to infinity, and from the right we're going to infinity. Negative 4 from the right, f of x equals infinity. So that means the limit as x approaches negative 4 is infinity. So now the only thing we have to do to check continuity is make sure that f of -4, that value is supposed to be infinity. Well, that value doesn't exist. There's an asymptote, so it does not exist. And infinity is not the same as does not exist, so it's not discontinuous at that point, and that is called infinite discontinuity. So I hope that made more sense of this confusing thing right here, and just know that the limit has to exist and it has to be the same as the actual value of the point. So at any other point on this graph, it is the same. Say we had the point -2, 2, say this was a point here. The limit as x approaches -2 from both sides is 2, and the point f of -2 is equal to 2 as well. So that's how we would say, yes, it is continuous if we had to prove it. So just know these rules right here and know what they actually mean in terms of a graph, and you'll be fine. Thanks for watching. Hope this was able to